last lecture we have started short circuit analysis of distribution system, and in the last lecture we have started with symmetrical component based analysis because you already know it. We have just revised it. However, there are many limitations of this particular sequence component based theory. So, in the particular last lecture we have seen sequence based analysis, where if there is any network, we have seen how to get the Thevenins equivalent sequence networks till your fault point, and then we have seen how to connect this particular sequence network if there are particular types of faults. So, we have seen there are three types of faults which can be analyzed using sequence networks connections, that is line to ground fault, line to line fault, and line to ground fault. Now, let us see what are the limitations of sequence component based analysis and why it cannot be used in distribution system. It can be used, however, there it will introduce error, and we will see what are the sources of errors in distribution sequence component based analysis. So, we have seen that distribution system is inherently unbalanced and untransposed, and as we have seen that in case of sequence component theory, one basic assumption is that system is balanced before fault and only positive sequence quantities exist in the network before the fault. So, that condition will not get satisfied in case of distribution system, because distribution systems are very much unbalanced before fault also. Also, there are many sections of the line which will be having single phase laterals or two phase laterals, or feeder section will be single phase feeders or two phase feeder. In addition, there will be some loads which are single phase load, some load will be two phase loads, and they are basically very much unbalanced. That is another problem. Due to untransposed line, there will be unequal mutual coupling between the lines, which leads mutual coupling between the sequence network. So, we have seen that if the line is transposed, in that case your impedance matrix will be having nature something like this: ZS, Zm, 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 Zs, Zm, 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 and Zfs. So, all the three diagonal entries are equal, as well as non-diagonal equal entries, that is Zm, they are equal, and if you convert them into sequence domain, we have seen that we get Z0, 0, 0, Z0, Z1, and then your Z2. And in this case, we can see that your Z0 and Z1, they are uncoupled. Similarly, Z1 and Z2, they are uncoupled. This is happening because we are considering for transposed line. However, if the line is untransposed, these Zms are not equal to each other. Similarly, these are not equal. So, in that case, your matrix will be something like this. So, it will be Z AA, Z AB, Z AC, Z BA, Z BB, Z BC, Z CA, Z CB, and Z CC, and all of them are different from each other. In that case, if you get sequence matrix, sequence impedances, it will not be only the diagonal entries exist there. In that case, it will be something like this: Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. So, you can see here, these sequence networks are not exactly decoupled. So, there is coupling between sequence network itself, and basically this will whatever advantage we are getting in case of transmission system, that systems were decoupled and you can easily connect them to fault current because there is no mutual coupling between impedances of this network. However, you can see that in case of distribution system, which are basically untransposed one, these impedances in sequence network, they are coupled with each other. Therefore, we are not getting exactly any advantage of using symmetrical components in distribution system. There are studies which are carried out by many people and which also tells us that symmetrical component will give non-negligible errors in distribution system short circuit analysis. Therefore, nowadays phase variable based short circuit analysis is more preferred as compared to sequence impedance based method. So, in this case we are not transferring our system into sequence domains. Basically, whatever analysis we want to do, we are going to do in phase variable domain itself. So, initially to start with, let us say one simple method we can consider, which is given in book of Cresting. So, here let us say you are having one source, then there is one say transformer, and then there is a primary distribution line, then another transformer which again step down, and then there is secondary line which goes, and here there is some fault has occurred. Okay. So, this network can be shown it like this. So, there will be source, and then there will be impedance of this source, then there will be, so it can be Z system I can show in the, because source will not be there in case of distribution system. This may be 33 kV network which is incoming. So, Z system, then this is Z transformer 1, this will be, then you are having impedance of your line 1, and then this will be, okay, this will be your impedance of transformer 2, and then you will be having impedance of your line 2. So, this network will be something like this, various impedances depending upon where the fault occurs, those many impedances will come into fault current path. So, there are possibility that fault may occur at 1, 2, 3, 4, 5. So, there are 5 locations where the fault can occur, and depending on where the fault is occurring, you can easily get the Thevenins equivalent circuit by adding those many impedances. So, basically you will get Thevenins equivalent 3-phase equivalent circuit, which will be something like this. So, you are having this say EA phase, and this is your EB, and this is your say EC, 3 sources of 3 phases. Then up to wherever the fault is occurring, that much impedance will come into picture. So, if the fault is occurring at 0.5, all the impedances will come into picture, and those impedances will be shown it like this, and they will be mutually coupled with each other because these branches, 3-phase branches, they will be mutually coupled. So, this is say ZAA, ZBB, ZCC, and there will be mutual coupling, that is ZAB here. This mutual coupling is ZBC, and there will be mutual coupling between these two, it is ZCA. Now, there will be some fault impedance which I can show it here. So, this is ZF, 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 which I consider as fault impedance, and then this is grounded, and this ground I have taken it here, this I am calling it a G point, and here I am taking one X point. So, this is your A phase, B phase and C phase, and this X point. This arrangement I have done, that is ABC and XG, so that I can create different types of fault into this network, and I can calculate fault currents easily. So, the fault current which this is IFA, fault current in V phase is IFB, basically this current, and this current is IFC. So, fault current IFA, IFB and IFC here. This voltage I am calling between A and X, it is VAX, between B and X it is VBX, and between C and X it is VCX, and between X and G it is VXG. So, for fault analysis purpose, we have converted this system into this particular system, and I have made this arrangement of this point x and point g and this point ABC, so that for different types of fault I can make different connections. So, let us write the equation for this. So, if you write the KVL equations for this particular figure here, so I can easily write on the right hand side there will be sources, this is EA, EB and EC. The voltage will be equal to the impedance drop across this impedances, that is ZABC. ZABC, as I told you, is consisting of impedances, 3-phase impedance matrix ZAB, ZBB, ZBC, ZCA, ZCB and ZCC, all the 3-phase impedances. They will get multiplied with fault currents IFA, IFB and IFC, plus there will be impedance drop across fault impedances, but fault impedances will not be mutually coupled with each other. So, they will be just diagonal entry fault impedances ZF, and this will again get multiplied with fault currents plus this voltage drop, that is VAX, VBX and VCX. So, it will be VAX, VBX and VCX plus this drop which is VXG, which is getting added in all 3 phases, which is zero sequence drop, basically VXG, VXG, VXG. Now, I am writing this equation 1 in just short form. So, this short form of this part of the matrix, I just write E A B C, which is basically this vector, which is equal to this total matrix, as I told you, I am calling it ZABC matrix, which is 3 by 3. This matrix I can say IF ABC, all the 3 phase quantities, plus this I can just say just ZF matrix, multiply again your IF ABC fault current, plus this matrix I can say VABCX, because all the 3 quantities, plus your VXG matrix. In this case, this is IFABC, so I can just combine this ZABC and Z fault, and I can just say it is Z equivalent. So, Z equivalent multiplied by IF ABC. So, I am just taking these 2 impedances together and I am calling it a Z equivalent plus VABCX, which is this quantity, plus VXG. So, I am just take this on next slide. So, basically what we have got is this one, EABC is equal to your Z equivalent into IF ABC plus VABC ABCX plus VXG matrix. Now, I am multiplying this whole equation with respect to Y equivalent, which is basically equal to Z equivalent's inverse. So, if I multiply with Z equivalent inverse with this whole equation, it will be Y equivalent multiplied by EABC. Here this will get cancelled out, so it will be IF ABC plus this will get multiplied with Y equivalent. So, Y equivalent into VABCX plus Y equivalent multiplied by your VXG. Now, here if you observe this quantity here, in this case y equivalent will be known because it is just inverse of z equivalent, and z equivalent we have seen that it is just fault impedance plus impedance of the lines. So, fault impedance and impedances of the lines, they are known, as well as Thevenins equivalent voltages EA, EB and EC, they are known. So, basically we can get this quantity, and this, since it is admittance multiplied by voltages, so it will be having units of currents. So, I can just say this will be IP ABC, which will be equal to IF ABC plus your Y equivalent into VABCX plus your Y equivalent into Vxg. Now, I can just write these equations in full form. So, in this case this will be IPA, IPB and IPC, all the three phase currents will be equal to, this quantity is fault current in A phase, fault current in B phase and fault current in C phase, plus this Y equivalent is admittance matrix YAC, YAB, YBB, YBC, YCA, YCB, YCC. It will get multiplied with VAX, VBX and VCX, plus again this Y equivalent is same, that is YAA, YAB, YAC, YBA, YBB, YBC, YCA, YCB, YCC multiplied by VXG, VXG, VXG. Now, you can see that if you observe this part of this equation, this YAA, YAB and YAC, they were getting multiplied with same term, that is YXG. So, I can just, this term of this equation, that is YAA into VXG plus YAB into VXG plus YAC into VXG. So, here I can just take VXG common out and it will be YAA plus YAB plus YAC multiplied by VXG. So, this I can call YSA. So, addition of these three, I am calling it YSA into VXG. So, this particular term will get this multiplied by this particular term will get multiplied by, so I can say YSA into VXG because 3 are same. So, then corresponding to this row it will be YSB into VXG, and this third row it is YSC into VXG, where YSB will be equal to YBA plus YBB plus YBC, and your YSC will be equal to YCA plus YCB plus YCC. Now, if you write these equations, so we have got this relation here, which is basically IPA, IPB plus IPC is equal to IFA, IFB and IFC plus your Y matrix, that is YAA, YAB, YAC, YBA, YBB, YBC, YCA, YCB, YCC multiplied by your voltages VAX, VBX and VCX plus, as we have seen that this part we have converted into VSA into YSA into VXG, YSB into VXG, YSC into VXG. So, it will be YSA into VXG, YSB into VXG and YSC into VXG. So, basically here are three equations which we can consider. So, this is equation number 1, equation number 2 and 3. So, equation number 1 I can explicitly write, it will be IFA plus YAA into VAX plus YAB into VBX plus YAC into VCX plus YSA into VXG. So, this is equation number 1. IPB will be equal to IFB plus YBA into VAX plus YBB into VBX plus YBC into VCX plus YSB into VXG. Say this is equation number 2, and IPC will be equal to IFC plus YCA into VAX plus YCB into VBX plus YCC into VCX plus YSC into VXG is equal to this is equation number 3. So, we have got these three equations from that last slide, which is equation number 1, equation number 2 and equation number 3. Now, let us see what are the unknowns which are available. As I told you, this part is available because this part we have got from Y equivalent multiplied by your Thevenins equivalent voltages, and since Y equivalent is known, which is calculated from impedance matrix of the line and fault impedance. So, Y equivalent is known as well as this one. So, this part is known. So, from these three equation I can just write IPA, IPB and IPC. Here the unknowns are actually IFA in these three equations, IFB, IFC, and these voltages VAX, VBX, VCX and VXG, they depend upon various faults. So, till we consider any kind of fault, let us consider them as a variable. So, VAX, VBX and VCX and VXG, they are also variable. So, if you put these variables, at least three equation into this matrix system. So, these three equations, so IAP is getting multiplied from first equation. So, IAP is 1, there is no term related to IFB and IFC, then here it will be YAA, YAB and YAC and YSA. So, this is first equation. Second equation, IFA term is not there, so IFB term is there, and then here Vx is getting multiplied with YBA, YBB, YBC and YSB, which is getting multiplied with respect to Vxg. And from the third equation we are having 0, 0, 1 here, then YCA, YCB, YCC and YSC, and say this is actually we are writing equation such that 0 will come on left hand side, and these particular 4 equations 1, 2, 3 and 4 we can get it from particular fault, because as I told you these variables VAX, VBX, VCX and VXG, they are related to, we have created in that equivalent circuit to create different types of faults. So, for different types of fault these variables will change, and these variables will basically give different types of faults. Let us say you are considering your LG fault into this circuit. So we can get these 4 equations for LG fault like this. So this system of matrix I am taking on next slide. So we have got this circuit matrix here, and if you are considering LG fault, so in case of LG fault, let us say your A phase is faulted. So in this case, since with ground, okay, so in that case your A phase and this will be grounded. Okay, so in that case I can say VAX will be equal to 0, as well as VXG will be equal to 0. Another thing I can say that there will not be fault current through B phase and C phase. So IFB will be equal to 0 and IFC will also equal to 0. So now we have got these 4 required equations which need to be added in this earlier system equations, where we have got 3 equations, and these 4 more equations we have got which can be put it here. So first equation, if I am putting it here, so it is corresponding to Vx is equal to 0. So Vx will come somewhere here, this will be 1, other elements will be 0, this makes Vx is equal to 0. Then another equation is Vxg is equal to 0. So from 2 Vx is equal to 0 means 1 will come here, all other elements are actually 0. And then third equation say IFB is equal to 0. So basically IFB means it will come here, 1 will come here, other will be 0. And fourth equation says IFC is equal to 0. So 1 will come here and other elements will be 0. So here we have got this system of matrix where this is unknown. So we can say this matrix is something like this. So this I can say it is X is equal to this matrix is Q corresponding to LG fault multiplied by this unknown matrix is say Y, and then you can get Y which will be equal to Q LG inverse into X, and as I told you Q LG is actually known. So we can get this fault currents after solving this. Let us say in case of LLG fault, how we can get these remaining 4 equations. So in this case, as I told you, 2 lines will be short circuited with respect to ground. So these 3 voltages will be 0. Those are, so say A and B is faulted with ground. So in that case your VAX will be equal to 0, VBX will be equal to 0 and VXG will be equal to 0. And one more equation we need, that we can get that fault, since there is no fault on space C, in that case your fault current in IFC will be equal to 0. So we can put this 4 equation into this matrix system. So first equation says this first, second, third and fourth. First equation says VAX is equal to 0. So VAX comes somewhere here. Second equation says VBX is equal to 0. So VBX will come somewhere here. 1 will be here. VXG is equal to 0. So this will be 1 and all other actually 0. And IFC is equal to 0. So there will be 1 here and all other entries are 0. So in this case also we can do the same thing. Let us see, this is your X matrix. This matrix is Q L L G and this unknown matrix is a Y. So we can get Y which is equal to Q L L G, whatever we are getting, its inverse multiplied by X. Let us consider one more fault, LL fault. So, in this case say line A and B are shorted. So, in this case say A and B are shorted means this will be shorted with respect to this line. So, I can say VAX will be equal to 0, VBX will be equal to 0, IFC will be equal to 0 because there will not be current, it is not faulted. And one more equation which we need that I can get, whatever this current IA will be opposite of IB. So, current IFA plus current IFB should be equal to 0. The addition of both the currents will be 0 at these locations because your IFB is coming from this side and IFA is coming from this side. This should be equal to 0. So, if you put say this is equation number 1, 2, 3 and 4, equation number 1 say Vx is equal to 0. So, this will be 1, other are 0. Second say Vbx is equal to 0. So, this will be 1, others will be 0. Third say Ifc is equal to 0. So, here it will be 1 and all other zeros. And fourth equation say IFA plus IFB will be equal to 0. So, there will be 1 here plus IFB and all other entries are actually 0. So, there will be 1 here and 1 here. So, we have got actually a required system of matrix equations, and as I told you we are considering this as X. In this case we can call it as a QLL because it is a real fault, and this is your Y matrix. So, in this case again we can get Y which will be equal to QLL and its inverse multiplied by X. And let us say your last fault, that is 3-phase fault, maybe it is grounded or ungrounded. So, in case of grounded also we will see. So, in case of 3-phase fault, in that case if the ground is not involved, this will be shorted, this will be shorted and this will be shorted. So, if 3-phase fault is occurring all the 3 phases, VAX will be equal to 0, VBX will be equal to 0, VCX will be equal to 0. And one more thing we can do is IFA, IFB and IFC, addition of all the 3 currents will be 0 because it is balanced fault. IFA plus IFB plus IFC will be equal to 0. So, this gives me equation number 1, 2, 3 and 4. So, in this case from first equation number 1 it will be 1 here, from equation number 2 it will be 1 yet multiplied by VBX, third equation there will be 1 multiplied by VCX, and from fourth equation there will be 1 here, 1 here, 1 here and all other entries are actually 0. So, this is how we can get the for 3-phase fault. And similar case, if there is 3-phase to ground fault, then all these 3 voltages they are getting short circuited. So, in this case we can say Vx is equal to 0, Vbx is equal to 0, Vcx is equal to 0 and Vx G is equal to 0. So, in this case there will be 1 1 1 entry, in this case all other entries will be 0. So, for particular fault we can get these remaining 4 equation, add to this system of equation which is written in matrix form and then call this as X, this is QLLLG fault and this is say Y, and then we can get Y matrix which is unknown, which will be equal to QLLLG fault, its inverse multiplied by X. So, in this particular lecture we have seen that how we can use phase variable based analysis, because we have seen there are some limitations of sequence component based analysis in case of distribution system. That is basically because of unbalance in the system as well as transposition not existing in distribution system. Moreover, there are some feeders which are single phase, two phase, three phase feeders, as well as loads also might be single phase, two phase, three phase. So, this creates problem or it introduces some kind of error in distribution system analysis based on sequence component based theory. That is why we have gone for phase variable based analysis. And phase variable analysis, we have seen one simple method based on getting equivalent circuit, and depending upon different types of fault, we can create system of matrix equations and solve it to get the fault currents. However, this method will be very cumbersome if the network size is large, because as I told you, we have taken very simple system to analyze the fault currents, but distribution systems will be having thousands of nodes, and if you are considering these thousands of nodes, and if you want to get this Thevenins equivalent network till fault point, it will be a difficult task. Therefore, we need to we need to analyze this fault systematically. So, in next lecture, we will see direct approach based method, which is very effective in calculating the short circuit currents, and which is based on phase variable method. Again, here also we are going to use, instead of sequence component, we are going to use phase variable based analysis. So, next time we will see that. Thank you very much.